you see omega P2 is greater than both omega P1 and P3 because it includes the transconductance gain GM. So being usually higher than the two break frequencies, omega P2 is sufficiently if omega P2 is sufficiently separated from P1 and P3, then the 3 dB frequency of the overall response, okay, the 3 dB frequency will be determined by the bypass capacitor at the source. Okay, so this will be omega P2. This will be omega P2 because it consists of the transconductance gain factor GM over here. So it's usually larger than the 2. So this means that the bypass capacitor determines the lower end of the midband. So you can see this in the figure as well. FP2 is greater than both frequencies, FP1 and FP3, and this determines the 3 dB response of the amplifier. Okay, and then you can also see that at each of the break frequency, the response, the roll-off factor adds to the response of about minus 20 dBs per decade, because you see then these factors are being multiplied. Okay, so if you plot the gain on logarithmic scale, then the roll-off factors of 20 dBs per decade is going to add for each corner frequency, at each corner frequency. So for example, the first factor has a roll-off of 20 dBs per decade. The second is going to add up in logarithm, okay, on if you take the log of these terms, then it will be minus 40 dB per decade. You combine 2, then if you combine 3, it will be minus 60 dBs per decade. Okay, but omega P2 being higher than P1 and P3 is determining your 3 dB frequency. Okay, so figure below shows the sketch of the low frequency gain of the common source amplifier, in which the 3 break frequencies are sufficiently separated so their effects appear distinct. Okay, so you see these are sufficiently separated. For example, FP3 and FP1 might be 5-10 times lower than FP2. Okay, this is on log scale. So, but FP1, FP3 are not much separated as compared to FP2. We observe that at each break frequency, the slope of the asymptotes to the gain function increases by 20 dBs per decade. So notice that FP1, P2, P3 are the frequencies of 3 real low frequency poles of the amplifier. These are the poles of the amplifier. They introduce the poles. So for example, when S is equal to minus omega P1 or S is equal to minus omega P2, minus omega P3, the function blows up. These are the poles of the transfer function. And these poles, they determine the 3 dB frequencies as well, and they contribute 20 dBs per decade for each pole, and this sums up with the other poles as well. Okay, so for example, at FP1, you're going to have minus 60 dBs per decade of roll-off. So and AM is the midband gain, which has to be about at 0 dB, and this FP2 determines the point where the midband gain falls to 3 dB of maximum. Okay, so as you are going to reach towards the midband gain, so in the vicinity of FP2 or the frequencies greater than FP2, well, the frequency dependence on these capacitors are insignificant. Okay, which means the midband gain. So the midband gain, you know that it's independent of frequency. So we are going to treat all these capacitors as short circuits. Okay, so to find the time constant and hence the break frequency associated with each of the 3 capacitors, the procedure is simple. The first thing you do is you reduce V signal to 0. Okay, so remove the signal source, then consider each capacitor separately. That is, assume that the capacitors are perfectly short, and then try and measure the resistance. So for each capacitor, find the total resistance seen between its terminal. This is the resistance that determines the time constant associated with the capacitor. So for example, what is the time constant that this omega P3, for example, for associated with the coupling capacitor CC2 is 1 over tau. Okay, I mean omega P3 is 1 over tau, which implies that tau is CC2 multiplied by RD plus RL. Okay, that is the time constant that is being contributed by the coupling capacitor CC2, and this is the resistance that appeared between the terminals of the capacitance. Similarly, for CC1, the coupling capacitor CC1, RD plus R signal is the resistance that appeared between the 2 terminals of the capacitor. Okay, so the time constant is 1 over the break, is 1 over omega naught. That's the break frequency. Okay. Uh, so how do you select the values for the coupling capacitors and the bypass capacitors? So we now address the design issue of selecting the appropriate values of the coupling capacitors, bypass capacitors. The design objective is to place the 3 dB frequency at a specified value while minimizing the capacitor value. So since as mentioned, but the bypass capacitor is the highest of the 3 break frequencies, okay, because omega P2 is dependent on the transconductance gain GM, it's given by GM over CS. So the bypass capacitor is very much effective in determining the 3 dB frequencies. So the total capacitance is minimized by selecting CS so that its break frequency is FP2 is FL. That is, we then decide on the location of the other two break frequencies, say 5 to 10 times lower than the frequency of the dominant one, FP2. However, the values selected for FP1 and FP3 should not be too low because that would require larger values of CC1 and CC2, and then that might not be necessary. Okay, so well, you can select FP1, FP3 5-10 times lower than FP2, okay, but not much lower because that would require unnecessarily higher values of the coupling capacitances CC1 and CC2. Okay, so this design example, this is 4.13, which takes the same values from example 4.12 that is discussed in the previous videos. So what we do is over here, this design example shows how you can select the values of the capacitances to select the break frequencies. So what we do is we wish to select the appropriate values for the coupling capacitor CC1 and CC2 and the bypass capacitor CS for the common source amplifier whose high frequency response was analyzed in example 4.12. So basically the parameters are very similar. The gate resistance is 4.7 mega ohms, same as the last time. Drain and the load resistors are 15 kilo ohms. R signal is 100 kilos. Transconductance gain is 1 milliamps per watt. So it is required to have the 3 dB frequency at 100 hertz and that the nearest break frequency at least a decade lower. So FP2 will be basically, okay, FP3 will be FP2 divided by 10. Okay, so it's required that since FP2 is the highest of both FP3 and FP1, so FP1 and FP3 are should be at least 10 times lower than FP2. So let's go ahead and find FP2 first. FP2, if you recall, is GM by omega CS. You have to divide this by 2 pi to find the 3 dB frequency in hertz. Okay, so this is GM. CS is GM over 2 pi FL, and FL requirement is at 100 hertz. So just go ahead and substitute those values, and we'll find out the CS is 1.6 microfarads. Then for FP1, FP2, FP3 is 10 hertz, which is 10 times lower than, a decade lower than 100 hertz. Just substitute for FP3 and FP2 and you will find out. So these values are, for example, this value is for 0.1 and 4.7 is RG. So you have this RG plus R signal. Okay, this is for the coupling capacitor CC1 at the source. Okay, you can see these values over here. So just substitute those values, they are given. So RG, for example, R signal is given. RG is 4.7 mega ohms and R signal is 100 kilos or 100 over 0.1 kilos. Okay, so you have to multiply this by CC1 and then 2 pi to find FP1, which is 10 hertz. Okay, so that gives you CC1, the coupling capacitor, as 3.3 nanofarads. And then similarly, you do the same for which consists of for CC2, which consists of RD and RL, which is the same resistance as 15 kilo ohms. So this analysis gives you CC2 as 0.53 microfarads. Okay, this is 0.53 microfarads, is 3.3 nanofarads. Again, CS is the dominant capacitance that determines the lower frequency FL. Okay, and that's the frequency where the midband gain falls to 3 dB. And then thereafter, the other breakpoints, they are going to add 20 dB per decade each. So roll-off factor increases at each breakpoint, and the other breakpoints are about 5-10 times lower than FP2, which is the 3 dB or the dominant corner frequency of the transfer function, okay, of the low frequency transfer function of the MOSFET. That's all. So you see, the idea was to show that these three capacitances, the bypass capacitance CS, and the coupling capacitance CC1 and CC2, the transfer function relating the output to input is very much dependent on the frequency, which is it's frequency dependent, which is due to the capacitive reactances of all these three capacitances, those coupling capacitances and the bypass capacitors. Okay, and these capacitances are introducing their own breakpoints, and they introduce, I mean, to make the overall transfer function a high pass type. And you see, at low frequency regions where the frequency is not much high, you cannot ignore the capacitive reactance. Okay, so it's not short circuit. The capacitive reactance is high, so you have to include it in the transfer function to find the to better reflect the gain of the amplifier, which is otherwise frequency dependent. Okay, because of the given coupling and the bypass capacitances, it's not like the midband gain, which is independent of the frequency. Okay, so you have to take it into the account for low frequency region. You have to take into account the external capacitances. But however, the internal capacitances for low frequency are to be considered as open circuit, because those capacitances between the gate and drain and gate and source, or the junction capacitances, or the order of picofarads, they are small capacitances, and the capacitive reactance can therefore be considered as an open circuit. So we are not considering the internal capacitances of the MOSFETs, just external capacitances over here, which are introducing frequency dependent gain transfer function between the output and the signal at low frequencies. That's all.